Okay, so welcome to the last part of 11.2. Um, I think we left off with a quick little example. So let's just kind of do another quick one here. Let's say P is at 2, -8, and Q is at -4, 0. And I want to find vector PQ in component form. Okay, so we talked about this in the first part of 11.2, but from here we see clearly we're starting at point P and our vector ends at point Q, so we always do the terminal x minus the initial x. So in this case we would do -4 and then subtract 2, and then we do 0 since that's where we end, and then subtract -8. So in component form, this vector becomes -6, 8. So in other words, a vector that's 6 units to the left and then 8 units up. So if this is 6 and this is 8, this is the vector that we are talking about, starting here at P and ending here at Q. Okay, so here's P, here's Q. Okay. So now, one more thing to add. So we talked about what a norm is yesterday. We know that that's just another way of saying the length or magnitude. And so let's say we have a vector v with components v1 and v2. Then the norm, which is just this notation, the length, and again now you can kind of see it with drawing the triangle like we did here. If we have a vector that's got a horizontal piece or a horizontal component of v1 and a vertical component of v2, well, you can see here that this length is just the hypotenuse of this right triangle, so it's not a hard leap to make that the length is just the sum of the square root of the squares. Oh, I said that backwards. It's the square root of the sum of the squares of the components. Okay, so just square each component, add them up, take the square root. That is the length or norm or magnitude. Okay. All right, so now we're going to switch gears. This is kind of where I wanted to get to yesterday, but I didn't have enough time. Let's talk about unit vectors. Okay, unit vectors are just vectors that have a length of 1. Okay, and in particular, there are 3, well, 2 if we're in 2 dimensions, but 3 if we're in 3 dimensions, very important unit vectors. So let's just go ahead and define them. So if we have our usual x, y, and z axis, if we take a vector starting at the origin and going out along the x-axis here, that is one unit vector that has a name. If we go 1 unit this direction, that's the second one. And if we go 1 unit this direction, that's another one. So if all of these vectors have a length of 1, okay, these are some very important vectors that we will use quite a bit in our calculations here. But let's start with this one here. In component form, if we start at the origin, you can clearly see that we're going 1 in the positive x direction, and then we're not going anywhere left or right or anywhere up or down. So this particular unit vector, this orange one here, in component form is 1, 0, 0. The name for that is the unit vector I. Okay. Similarly, this pink one here does not have an x component. It has a y component of 1, and it has an OZ component. That one is called J. And we put a little vector symbol above it. In 2 dimensions, I and J are usually the ones that we need to worry about. But once we throw in a 3rd dimension, this Z dimension, then we have another similar vector, that's 0, 0, 1, and the name for that is K. Okay, so these are the 3 unit vectors that we will use quite a bit. And what you need to be comfortable with is the concept that every vector in 2 or 3 dimensions, so in 2 or 3 space, can be uniquely written in terms of I, J, and K. Okay, and if you're wondering, well, how does that work? Okay, here's a quick little proof or argument for it. So let's say that we have a vector V with components V1 and V2. Okay, well, we could argue that this is maybe the result of 2 different vectors, one that solely has a horizontal component of V1, so then the y component would be 0, and then another separate vector that has nothing for the x component, but V2 for the y component. So here you can see that if you add these 2 vectors together, you get V1 comma V2. Okay, and now if you factor out V1 from this first vector, that leaves you with 1 comma 0 as the vector left over. Well, 1 comma 0 is just the unit vector I. Okay, we don't have the extra 0 there because we're only in 2 dimensions, but this is the same as I, and if I factor out the V2 from the second one, we get 0 comma 1, and that's the same as the unit vector J. So any vector V that has components V1 and V2 can be written as V1I plus V2J. Okay, so this here with the brackets is component form. And this notation here is IJ form. Or if we had 3 dimensions, we'd have IJK form. You should now be able to comfortably switch back and forth from these 2 forms. So, for example, if we have the vector 2, 0, 3, that's the same as 2i plus 0j, so I'm not going to write that, plus 3k. And vice versa, if you have a vector that's in ij form, so maybe something like, 2i minus 5j, you should know that that's the same as 2 comma negative 5 in component form. Okay? So hopefully that makes sense. And now moving forward, we can talk about what it means to normalize a vector. So as you'll see once we get going with more applications, one of the things that's very important is normalizing a vector, and that might be just part of a longer process or a longer problem where in order to get things started you first have to normalize, or maybe that's part of the answer at the end, but what it means is to find a unit vector in the same direction as a given vector. And we'll call that given vector v again. Okay? So again, the concept here, pretty simple. So let's say v looks something like this, and it has components, v1 and v2. Okay? So if v equals v1, v2, how do we make this vector have a length of 1? Well, why don't we step aside just for a minute and let's look at an easy example. So let's say we have the vector 3, 4. So that's 3 to the right, 4 up, and now here's v. Well, hopefully you remember from geometry that this length, either by Pythagorean theorem or triples, the magnitude of v is 5 in length. So this side is 3 in length, this side is 4 in length, and then this side here is 5 in length. Well, what it means to normalize this vector is to shrink. So instead of being 5 units long, which is how long this currently is, we want to shrink this down so that it's just 1 unit long. So from 5 units, we want to make this 1 unit long. And what that does is create this tiny little triangle in here that's similar to this larger triangle that we have here. So to get from 5 to 1, we're just dividing this length by its length, which is 5. So 5 divided by 5 is 1. And if we divide this hypotenuse by 5, the leg has to get divided by 5, and so does this leg. That has to get divided by 5. Okay, so now this little baby vector, which, same direction, but only 1 unit long, let's call it u. U for unit vector is going to be 3/5, 4/5. Okay, so to summarize the process, the first thing you have to do given any vector is figure out how long the vector is, which is what we did here. We figured out it was 5. And now you just take the components 3 and 4 and divide it by that length. So that's how we got 3/5 and 4/5. So in general, if we have a vector v with v1 and v2 as its components, to normalize a vector, you could just argue that you divide each component by length of v. So our unit vector is going to be v divided by the length of v. Okay? So real quick, let's try another example here. So let's say we have a vector with -4, 6, and 5 for the components. We want to find a unit vector in the same direction. Okay, so first we want to find the length of v. And now that we've talked about this before, we know that to find the length, you just take the square root of the squares of all of these added together. So that's 16, 36, 25. So that's root 77. And so now the last step here is to take v and multiply by 1 over v, or divide by v, the magnitude of v. Okay? So just take the components, -4, and you divide by root 77. Same thing with 6. Same thing with 5. Okay? And if you do not believe that these three components give us a unit vector that is 1 in length, you could verify by squaring this component, squaring the second one, squaring the third component, adding them all up. You'll get 1, and certainly the square root of 1 is 1. So the length here will check out. Okay? All right. Almost done. Next we have the topic of vectors that are determined by length and an angle. So again, let's say we have, here's our normal x, y plane, but here's v. And let's say that we have an angle with respect to this positive x-axis. Let's say that angle is theta. Okay? Well, we can figure out what v is using some trigonometry. So if you make a little right triangle here, so here's your horizontal component, and here's your vertical component, okay? Using some basic right angle trig, you can figure out that this adjacent length is going to be the magnitude of v, the length of v times cosine theta. Okay, and if you're not sure where I got that, again, so let's say we're looking for the horizontal piece here. This is theta, and we know that this is the length of v. We know that the cosine of theta is adjacent, which is h, divided by hypotenuse. And so you can manipulate, certainly, and now you see where that comes from. The magnitude of v times cosine theta gives us this length here. And similarly, this length here, the opposite side will just be the length of v times sine of theta. Again, you can just use right angle trig to figure that out. So, in other words, since I know that this is my horizontal and this is my vertical component, you could say, well, this vector can then be written as length of v times cosine theta times I plus length of v sine theta times j. Okay, so that would be an ij form. Of course, you could also write that as in component form. So first component is magnitude of v times cosine theta. Then we got magnitude of v times sine theta. You might even see that since this is a common length, you can factor it out. And so now this is the same as just cosine theta sine theta, which is interesting because when you factor out this length has a length of v. The length of this vector has to be 1 now. Okay, when you can verify that, cosine squared plus sine squared is 1, so that's kind of interesting there. Think of it that way. So this is a unit vector right here. So anytime you're asked to find a unit vector in a given direction, if you know the angle, it doesn't matter how long the vector is. If you know the angle with respect to the x-axis, it's simply the cosine and the sine of that angle for the unit vector, which is kind of a nice thing to remember. Okay. All right. So the very last thing that we're going to do Actually, let's do one example before we wrap up with the resultant of forces. So let's say we want to find the components of a vector v with a length of 7 along the line, from 0, 0, 0 to 3, 2, 2 root 3. Okay, so here we are starting at the origin. We're going out a little bit, right a little bit, and then up a little bit. And we want to find, so if we draw this line in there, we want to find a vector that's along this line, but that has a length of 7 units. Okay, and the easiest way to do that, anytime we have a problem like this, is to first figure out, since we have this starting point and we have a point on the line, we know that a vector that's on that line, if you just do the component form, take final minus initial for all the x and y and z coordinates, you get that there's a vector that has 3, 2, and 2 root 3 for the components. Okay? Now, I don't know what the length of that is. My guess is that it's probably not 7. Okay? But let's go ahead and find it. Well, the length is just going to be the square root of the x component squared plus the y component squared plus the z component squared. And if you add that up and take the square root, you get that this length is 5. So not quite 7, but it is 5 in length. And so now there's several ways to approach this, but probably one universal way that'll work is to let's go ahead and just write down the unit vector that's related to this vector. And to do that, since we know the length already, you can just take all the components and then divide them by 5. And so now remember that this is 1 unit in length. If we want this to be a length of 7, you can just multiply by 7. Okay? So just multiply this unit vector by 7, and now we get a vector that is 7 in length. And so your final answer here will just be 21/5, 14/5, and 14 root 3 over 5. And again, you could verify that. Square each one, add them up, take the square root. You should get 7 there. Okay? All right. So the very last thing now that's in this vector introductory section is something we talked about earlier, which is just adding vectors together, but now let's actually look at an application. So this is specifically the resultant of 2 concurrent forces. Okay, and so imagine that there are 2 forces acting on an object. Easiest thing to do is just position that object at the origin. Okay, but let's say that we have one force acting at a 30-degree angle. Let's call it F1. Let's say that the length of that vector, that force, is 100 newtons. Okay? And let's say we have another one we'll call it F2. And let's say that this length is 300 newtons. So this force has 300 newtons, this one has 100. And let's go ahead and say that this is a 30-degree angle, and that this here between the blue and the pink is another extra 15 degrees. Okay? So now, what it means to find the resultant is just to add them, okay? So I'm kind of skipping the formal description of the problem, but it would say something along the lines of, here's this object centered at the origin. There's two forces acting on it, F1, F2. So imagine maybe, this is a box and you got one force pushing it that direction with that magnitude and another one pushing it that way with that direction, magnitude of 300, okay? I think you guys can see that the overall motion is going to be something in between these two. Okay, so if you actually drew, here's F1, and then you connected F2 with it, here's what we're looking for. We're trying to figure out what this vector is. This is F1 plus F2 right here. Okay. Now the easiest way to do that, or at least one method that should work no matter what, is to first go ahead and figure out what F1 and F2 actually are. Because we don't really know them, we just know the angles and we know the lengths. The nice thing is that we've talked about that if you know lengths and you know angles, we know that the vectors are just going to be the length times the cosine of the angle made with the x-axis here. So this is just going to be times cosine 30 times sine of sine of 30. F2 has a length of 300, and the angle with respect to the x-axis would be this 30 plus 15 degrees, so that's a total of 45. Okay, so if you go ahead and write out what this looks like, remember that from the unit circle, the cosine of 30 is root 3 over 2, and the sine of 30 is 1/2. The cosine and sine of 45 degrees are both root 2 over 2. So if you simplify them, you get 100 divided by 2 is 50 root 3. And then this one, the y component is just 50. So here's F1. These are the exact components for that first force that's 100 newtons in length. And for the second one, it's going to be 300 divided by 2, which is 150 times root 2. And that'll be the components for both x and y. Okay? So now to find the force, we need to know a length. So we want to add the two vectors. And we've talked about that now. That's pretty simple. To add two vectors together, you just add the components together. So for the resultant x, you just take the first x and the second x and you add them up. So you get 50 root 3 plus 150 root 2. And then for the y component, it's 50 plus 150 root 2. Okay, so there's my resultant of the two forces acting on whatever object I have here. What we need to do now is find the length. So what does the vector look like? What does F1 plus F2 look like? So for that, we need a length and a direction. Just like this initial force here, we knew that we had a 100 Newton force that made a 30-degree angle with the x-axis. Here we had a 300 Newton force that made a 45-degree angle with the x-axis. We want to figure out how long the resultant force is and what that angle is with respect to the x-axis. Okay, so to find the magnitude, we're going to do exactly what we did before, which is to take each component and square it. Okay, now I'm going to be a little lazy because I don't want to make this video longer than need be. But I'm going to take the x component. That's going to get squared. I'm going to take the y component. That's going to get squared. Okay, and if you type that in the calculator and get an approximation, that ends up being about 397.44 newtons. So there's the length. So if I have this 100 and 300 Newton force acting on this object, the final force, the resultant, is just shy of 400 newtons total. And now the angle that we're going to get has to be between 30 and 45, somewhere in between, right? Here's how we can find that. We know the y and the x component. So if this is F1 plus F2, we know what the x component is because we have it right here in that pink circle, and we know what the y component is. And we're looking for this. So if I have the opposite side and I have the adjacent side, and I'm going quickly, but hopefully this makes sense, we know that the tangent of theta will just be the opposite side, which was the vertical piece of F1 plus F2, divided by the adjacent portion, which is 50 root 3 plus 150 root 2. Okay? And now that you have that, certainly you could do the inverse tangent of this on your calculator, and you get about 41.27 degrees. Okay? So there's a little bit more examples that go along with 11.2, as well as some additional concepts that we didn't have time to finish. I hope you have a good weekend. That is it for 11.2.